This is our star, the Sun. It's a star I'm feeling the radiation of right now, and unless you're watching this at night or you're an alien intercepting this in a distant galaxy, chances are you are too. This is the investigation of how the universe was transformed from a load of pointless gas like this to this. It's a journey that will take me to every corner of our infinite universe, bus routes and the green screen effects of iMovie would allow. And I'll be asking questions.
We know the moon is made of cheese. What kind of cheese? Is there a lactose-free section?
To leading academics, experts, and nerds who will help me unlock the mysteries of the universe. So join me, Ella Phunt, for a cosmic look at the bright universe, the tiny dots that have been fundamental interests of human man since we started saying oak. More specifically, stellar spectra. This is Phunt On Earth.
For thousands of years, we had no idea about the stars above our heads. Nowadays, we have a small piece of the puzzle that is the workings of our universe. From nerds and middle-aged white women who always carry crystals.
Stellar spectra are the results of the transitions of electrons in atoms and ions that take place in stars. When an electron jumps up an energy level, like a small child having a lolly and running up these stairs, it gains energy. However, when the electron jumps down an energy level, like this, good God, it releases energy, just like I did when I screamed. That energy is released in the form of light.
As this light is emitted, some wavelengths are absorbed by the atoms on the outer layers of the star, leaving dark bars when the light is viewed through a spectroscope like this.
What is the sun made of? My mate Daryl tried to look at the sun a bunch and see if there were any aliens turning it on and off, but then he suffered serious vision loss. What's in there? Why are they trying to keep this information from us? Well, the sun is made predominantly of hydrogen and helium, and we know this from the absorption lines in stellar spectra. So each element has its own fingerprint per se, and the lines we see are different for each element. Koalas have fingerprints too, you know. Do you think there's ever been a koala serial killer, and that's why we haven't found him? Do you think he's hiding in the sun? I don't think I'm qualified to give information on that. So if there was a koala in the sun, would it be very warm? Because it's cold in space. Can we check his temperature in space post him a jacket? Well, I am almost certain there isn't a koala in the sun, but we can investigate the temperature through the relationship of the intensity of the star and the colour of the star. Thank goodness, I'm getting pretty worried about the koala. Right. Okay.
Surface temperature of a star is different to the temperature of the star's core. For example, a supergiant, very big, whose core temperature is much higher than that of a white dwarf, would have a much lower surface temperature because it is so big it's stretching that energy out. The relationship between a star's surface temperature and core temperature is determined by its radius and surface area. This is because the surface temperature is dependent on the intensity of radiation at the star's surface. Intensity, I, is given by P over A, which is power or luminosity of a star, and A being the surface temperature. Stars with a large surface area, like supergiants, usually have a large difference between their core and surface temperature. Despite the high luminosity, a supergiant star has a low intensity of radiation at its surface because it is so much larger and it has that large surface area. Since the colour is mostly determined by the wavelength of light with the greatest intensity, which is also known as the peak wavelength, or as we see on this diagram, lambda max, Wien's displacement law can be used to analyse the relationship between colour and a star's surface temperature. This is Wien's displacement law. So lambda max equals B, which is the constant 2.898 times 10 to the negative 3, and T, which is the surface temperature. A star's colour is determined by the peak wavelength. So if the peak wavelength is very short, it'll fall in this blue section, so the star will appear blue. If it's very long, it'll appear in this red section and the star will look red.
Is there much room for the koala? Is it cramped?
Again, there is no koala, but we can determine the density of stars from the stellar spectra. The increased gas pressure in higher density stars causes atoms to collide more often. Electrostatic contact between the orbits of various atoms caused by these collisions alters the energy level of the affected orbits, like how we were on the playground earlier. The wavelength of the absorption line decreases as the energy state of the orbit rises, meaning it has more energy. The wavelength of the absorption line increases as the energy state lowers, it has less energy. Absorption lines become wider and fuzzier as a result of the combined impact of these modifications. The universe has been continually expanding since it began, but it's still infinite. A way to think about this is that the universe is a load of little dots like this. They go on forever, I just couldn't be bothered to draw the rest of them. So there's these dots that go on forever, and these are points in space-time in the universe. Now, as the universe expands, the space between these dots gets bigger. The dots themselves haven't necessarily moved, it's just that the space has expanded between them, and the dots haven't gotten bigger, but that is how space can be continually expanding and still infinite.
How fast is everything expanding? Should I be measuring myself to see how much I'm growing?
When we talk about galaxies expanding, we're speaking about a massive scale. Entire galaxies are moving away from us very quickly, so no, you shouldn't be measuring yourself. It just wouldn't be noticeable.
How do we know they're moving away very fast? Are you sure I couldn't beat them in a race?
No, you definitely could.
No?
No. And we know that they're moving away from us through redshift. The emission spectra shift to the red side. The amount of shift tells us how fast it's moving. So if it was only shifted a little bit here, it wouldn't be moving very fast. But here, because it's shifted a lot, we can tell that it's moving very, very quickly away from us. If the galaxy was moving towards us, the lines would be blue shifted, like down here. So the emission lines would shift towards the blue spectrum. The reason for this shift is the Doppler effect. So as it moves further away, the wavelengths of light lengthen, which translates to the colour red being more prominent.
As galaxies spin, different parts are red-shifted and blue-shifted. Take me on this carousel. When I spin this way, I move away from you. But as I continue spinning, I unfortunately move back towards you again. It's like my relationship with my ex-boyfriend Jack. When I move away from you, I'm red-shifted because I'm mad because Jack has said something really stupid. But when I come back towards you, I'm blue-shifted because I'm sad and I miss Jack, which is a wonder because he's an absolute.
But if galaxies are both red-shifted and blue-shifted, how do we see that on stellar spectra? Well, as the galaxies spin faster, the lines get thicker. But as they move away faster, they shift to the red side. This is the emission sample we have on Earth, where there is no shift. So this galaxy is spinning fast, but not moving away very fast. And this galaxy isn't spinning very fast, but it is moving very quickly away from us. Useful thing, this stellar spectra. It is, yes. Stars are put into different classifications that can be seen on this HR diagram. Why do stars have a human resources diagram? Is it because they keep making such controversial hot takes? It's Hertzsprung-Russell, not human resources. And
Who the hell are they?
well, they're the two people that are credited with the diagram for star classification. The HI diagram shows temperature, spectral class, and luminosity.
How does it do that? Hasn't it only got two axes? Axae?
So we have values on all four sides of the diagram. Here on the left, we have the absolute magnitude, which is how bright it is. Not how bright it appears, that's apparent magnitude, but how bright it is. And on the right, we have the luminosity compared to the sun. So it's the same values, but just different ways of measuring and different sort of scales. On the HR diagram, we see where a star is in its lifestyle. So we have supergiants, giants here, and then these main sequence stars, which is almost like a belt going through the middle. And then down here on the bottom left, we have the white dwarfs, which are hotter but less bright. The HR diagram also helps us in knowing things about evolution of stars. So as stars start out, they start as a stellar cloud with protostars. Then they kind of only have two options: small star, large star. Keeps going, and eventually you'll end up with either a white dwarf, a neutron star, or a black hole. Trying to see how these all interconnect can be a bit tricky on the HR diagram, but luckily we have arrows. Here we have a Hertzsprung-Russell diagram, a bit less colourful than the last one, I know, but I still think it looks nice. And we can see through these arrows how stars move between their types. So here we have a lower temperature star which has only a 0.1 solar mass, but then it moves to a higher temperature, going through as a red giant, so it expands and gets bigger, then moving through to a main sequence, simmers back down, before finally going all the way smaller to be a white dwarf. As you can also see from this diagram, it's very common for stars to sort of shrink down rather than get bigger, in which case when they are getting bigger, they are moving up and they're expanding, and then they will return back down and eventually become a white dwarf or a black hole, because that is how stars live out the end of their lives. And what about this auto-generated password at the bottom? So this auto-generated password down here at the bottom is the spectral class, which is opposite the effective temperature. The effective temperature is in Kelvin. It's how hot it is, basically. They're very hot, they're stars. And the spectral class tells us different things about that temperature. It tells us the colour, luminosity, size, and we all gather that from stellar spectra.
How do you decide which stars are which classification? Like my ex Jack once tried to mix a ton of different pasta together and then got upset when some were undercooked and some were overcooked. The type of star impacts how long it cooks for and how hot it is, right?
Yes it does.
And that's from a professional Jack.
Yes, I'm very professional. The type of star is dependent on the temperature, mass, colour, luminosity and size. This is another way we can tell what elements a star is made up of. Astronomers use spectral classification to classify stars based on spectral characteristics. Spectral characteristics help astronomers extract more information about the stars: elements, temperature, density, and their magnetic fields. Spectral classification and stellar spectra have helped us figure out what the universe is made up of, what are its workings, and these will continue to help us far into the future.